Hi there, everyone. Today we're going to talk about electricity. This is the beginning of the test material for Test 1. So, Test 1 material begins right now, this very second. And it will continue through this whole lecture until next week. And then in 2 weeks, we'll have a test. And that test is going to be about the same difficulty as the quizzes, which I've quizzed you on all the material so far. But we're going to have a test. It's going to be individual. You do it by yourself, with me watching or at the Workforce Center. So it's not going to be open book. It's going to be closed note. So just to reiterate, closed note, closed book, Workforce Center, or in class, which I'm going to prefer in class because it's easier for you guys. And I'm going to have my mentor, full-time professor, help me make sure it's not too easy or too hard. And remember, you can always email me, as you can see on the right side of your screen there, left side of your screen. You can always email me anything, and I usually get back to you pretty fast. I get it right here on my phone, on my Outlook app, usually instantly. Then on the right side of your screen, you can see the SI instructor's availability. She's usually very helpful, and sometimes you can catch her with no one in the room, so she can actually help you with your homework and help you get an A. And remember, no food or drink in the lab, and cell phones must not be out in the open. If you get a call, you can walk out of the room, of course, or you can check it real quick on the side of the room. We just don't want you getting any chemicals on your phone than on your face. So today, we are talking about electricity. To start, electrons are where everything is in this lab. They are responsible for the electricity. So that's important. And electrons have a net negative electric charge. They have a negative electric charge. And they may move. They're attracted to these nuclei, as you can see on your screen. But because the nuclei have protons and neutrons, so the nucleus have a net positive charge and electrons are negative. So they're attracted to each other. So these electrons are spinning around this nucleus like they're a moon or like they're Earth orbiting the sun. So they're attracted to it. But they can fly away to other atoms close to them. And it's this flow of electrons that causes electricity. It's the movement of electrons between atoms. So atoms, to go back a little bit, atoms are composed of protons and neutrons and electrons. Electrical, light, and chemical phenomena involve electrons. If you want to try to guess what nuclear reactions are, they involve the nucleus. So we're not gonna have any nuclear reactions in your laboratory, unfortunately. But if you look at if you want to know what a nuclear power plant looks like, you can look at the power plant in Rockport. That one was modeled after a nuclear power plant. So it looks just like one, although it's a coal power plant. And also remember that all electrical charges, this is going to be very important this lecture, all electrical charges are surrounded by an electrical field. So if something's charged, like you turn on the electricity to a cord, or to a wire, or to anything, there's going to be an electrical field around it. Might not be that strong, but there's one around it. So because there's that electrical field around that charge, it can be classified as a force because you can attract or repel other charges. So like charges are going to attract, like charges are going to repel, and unlike charges attract. Let me make sure I'm recording. Yep, I'm still recording. Okay, this creates a force. So ordinary atoms are typically neutral because there is a balance between the number of positively charged protons and the number of negatively charged electrons. So a physical or chemical reaction occurring can cause an atom to gain or lose electrons. So if an atom loses electrons, so if it loses a negative charge, which is an electron, let me just do an example. So let me look up carbon. Periodic table. Carbon is going to be 6. Of course, it doesn't tell me how many protons and neutrons. So let me just make up something. So we have, say like we have an atom that has 6 protons and 6 electrons. If it loses an electron, it then has 6 protons and 5 electrons. So 6 minus 5 is 1. So it has more protons, and protons are positive. So it's plus 1 charge. Plus 1 meaning positive. So it would then be classified as a positive ion. Now, if the same atom went and it then went to 6 and 5, or wait, 5 protons and 6 electrons, well, in this class we're just dealing with electrons. So we'll say it gains an electron. It would have a negative charge and be a negative ion, if you can get that. So now we're going to talk about static electricity. This is what stings you when you shake someone's hand or when you touch a door handle. So let's say that you're getting out of your car and you rub across the car seat. You gain a charge on you from that car seat, from the friction. And you're walking to the building, to the Ivy Tech building, and you grab the door handle to the Ivy Tech building. And you haven't touched any metal yet because you closed your car door with your foot, say. So you grab that door handle and you get shocked. Where'd that come from exactly? Well, it could come from 2 different places. Either that door handle was charged, but more than likely you gained a negative charge from the car seat. So it's important just to know that you gained a charge from the car seat, and that charge was electrostatic, which is going to be that first blank there. So it's an electrostatic charge is one that is on an object and is not moving. So the charge is at rest. So right after you got that charge from the car seat and you started walking to the building, that charge that whole time was electrostatic, meaning it wasn't moving, it was at rest. It was static on you. It was stuck on you, it wasn't moving, it's electrostatic. So an object can become electrostatically charged 3 ways. You're not going to be tested on this because it's a little too confusing, but it's either by friction, contact with another charged body, or induction, which is no transfer of electrons. That's kind of like when you charge a balloon and you put it up against the wall. The balloon's attracted to the wall even though it didn't give it any electrons. So what that balloon did was it pushed electrons away at the wall, and there's so it was positive. The wall ended up positive for a second, and the balloon was attracted. So most charges, once charged, most charges will return to neutral. Remember that. That's why the static electricity is flowing. It's trying to find a place to rest where there's an equal number of electrons and protons. So today we're also going to talk about conductors and insulators. So what is an electrical conductor? Best example is metal. Metal of a doorknob, metal wires, metal anything. Because metal usually freely shares their electrons. Now, every metal is going to conduct electricity a little bit differently. But then you also have insulators. You have plastic or wood. Now, what's an insulator? An insulator is going to go around the metal wire. It can still be charged, like with static electricity, but it's not going to conduct electricity as well as a metal. So you coat wires with insulators to help prevent fires, help you from getting shocked, and whatnot. Insulators are everywhere too, because you coat metal wires with insulators. So these electric charges kind of create a magnetic field around them, just like this bar magnet here does. So as you can see, those lines represent the magnetic field. Only in this case, it's an electromagnetic field. Those are field lines there, and as the lines get closer, when they get closer to the bar magnet, they're stronger. Okay, now we're going to talk about energy, electrical potential energy. So when two charges are brought together, this changes its potential energy. How do you measure this? With joules. But when we talk about energy, we take it a step further and we go joules per coulomb. Now, what's a coulomb? I do have a video on this that's really nice. Another guy explains it. That's what I try to do sometimes, is hit you twice. I try to explain it, and then I also provide a video off YouTube where it's really nice that another guy can explain it. For some reason, a lot of those turn out to be foreign speaking people, which is kind of funny that I always find videos like that, but they're great. So in this case, of course, we're going to measure energy in joules, just like with a steam engine. But we want to know how many joules per coulomb we're using. So we're measuring electrical potential difference. The work to create the potential divided by the charge moved. The work to create the potential divided by the charge moved. The charge moved is in coulombs, so it's joules per coulomb. So if I go from 6 volts to 12 volts to 24 volts, just imagine that the bottom is just 1 coulomb. 1. But the top goes from 6 to 12 to 24. So which one's stronger? I should say, which one has a higher energy? The 24 volts. Because there's 24 joules per coulomb. So it's good to kind of imagine the bottom as being 1 coulomb. And now you ask, what is a coulomb? Well, it's a metric unit of measure. It describes a quantity of charge. If you want to imagine it as a big bag of electrons that's in a battery, when you turn that battery on, these little electrons go running around the circuit. And when they get to that light bulb, they power up that light bulb. And they use some energy to do it, and then they run back around to that battery. So unlike kilograms and meters, which I can get out a yardstick or get out something that weighs 1 kilogram and show you those two, and you would know those in a heartbeat. It takes some time to digest and learn what a coulomb is. It's 6.25 times 10 to the 18th electrons. I'm not going to ask you to recite that on the test, but I would like you to recognize the difference between, or recognize if I printed it, what it is. So I'd like you to visually recognize 6.25 times 10 to the 18th electrons is 1 coulomb of electrons. So electric current, like I just said 2 slides ago, electric current is the result of flowing from a higher potential energy to a lower potential energy. So it's comparable to flow of water. You're going to start off really high, like a hydroelectric. Imagine a hydroelectric dam. All that water on top of it has higher energy than the water on the bottom, because in the middle, the water flows through, turns a turbine, and it creates energy. So, and if you had a hydroelectric dam in a lake, it's not going to work too well because the two sides are going to be the same. And so the water's not going to flow and nothing's going to be created. So you have to keep a separation of charge, which is right there on the line. To maintain current, you must maintain separation of charges. For instance, and also a good way to think about electric current is a mild example of the static electricity. The current flows from your car seat to your butt, through to your hand, to the door handle, to the next metal that you touch. So energy flows from a higher potential energy in the battery through the circuit, does work, then back to the battery. So work done per unit of charge is what? Work done per unit of charge. The work is in joules. The unit of charge is in coulombs. So joules per coulomb. That's a volt. That's right, it's a volt. I hope I'm not going too fast, but I guess you can always pause it. Okay, so we have voltage that I've been over and amperes. Amps. So voltage, like I said, it can be referred to as an amount of energy being used. An amp can also be referred to as how many coulombs are moving per second. So a coulomb, so an amp is a measure of how fast those electrons are moving. Imagine that example I gave of how a battery has a bag of electrons in it, and those electrons are just running out of the battery into that circuit and around. So imagine that an amp is a measure of how fast those coulombs are moving per second. You can also define that as the rate at which charge flows through a cross-section of a conductor in unit time. So there's that ugly word again, rate. Usually rate is per second. So you need to remember what an amp is. An amp is the rate at which charge flows through a cross-section of a conductor in unit time. So 1 amp equals 1 coulomb per second. So go back to the volt. Volt is 1 joule per coulomb. An amp is 1 coulomb per second. Very different. It's described more in this video right here. I'm not know if I'm allowed to show it right now, so you can watch that on your own time. And I would recommend you watch that 3 or 4 times between now and the test. I think it would be really good. You probably won't, but okay. So when we talk about this current that moves, there's 2 types of moving current. And now I just described the battery, which is the best way to think about how current moves through a circuit. But there's 2 types of current, 2 types of ways that those electrons move through metal wires. You have direct current, which is like car batteries, fuel cells, and solar cells. Electrons move one way. And you have alternating current. So, alternating current, the electrons move. They jiggle back and forth really fast. If you want to imagine, electrons just move one way, then the other. One way, then the other. And we'll talk about the history of it later. But AC works a lot better at moving electricity over long, long distances. So it'll be created at the power plant. It'll be stepped up on those big power lines you see next to like interstates. And it'll be stepped up, and that's almost like an interstate for the electricity. Then as it gets closer to your house, it slows down at transformers. And then once it gets close to your neighborhood, it slows down again. So remember that car batteries, fuel cells, and solar cells power direct current, or they use direct current, and AC is used by most of the electrical industry and electric utilities. Now, one neat thing is that DC is used to power landline telephones. And another thing, if you have a solar cell on top of your house, the sun hits the solar cell, so sunlight's converted to electricity in the form of DC, direct current. It goes into your house, it's converted to AC, then it flows throughout your house. A lot of appliances will have DC, so you're going DC to AC back to DC, and it gets really confusing. And there's a lot of energy wasted when you switch from DC to AC back to DC. So that's just a little knowledge FYI. Let's see how many slides we got left. We're about halfway through. So let's see. I had to just restart my internet. We should be back up. Okay, so now we're going to talk about electrical resistance, because those electrons that are moving through the current, they're going to bounce back and forth a lot, because they're literally small, they're charged, and they're flowing at a fast rate through that wire. So they're going to bounce back and forth a lot. When they do that, sometimes they waste energy. And this wasted energy is a measure of resistance. So the unit for resistance of volt per amp is the ohm. OHM. The ohm. So resistance equals volt divided by I. I is current, which is also amp. So the unit for resistance of volt per amp is the ohm. And I'm going to have an example of that later. And if you ever need to solve for volt, just remember volt equals IR. And I'm going to have a separate video on how to solve equations and a separate video on significant figures here coming up too. So, electrical resistance of a DC electrical conductor is measured 4 different ways. You got the material of the conductors. That's going to be like the type of metal. That's pretty straightforward. You got the length. So the longer the wire, the more resistance, and vice versa. You also have diameter of the wire. Now this is a little tricky. The thinner the wire, the greater the resistance. That's because you're pushing the same amount of charge through a thinner wire. Imagine comparing a 6-lane road and a 2-lane road, and you're trying to fit the same number of cars. You're going to have trouble. Temperature. Usually resistance increases with increases in temperature. That's because the electrons bounce around a lot more. And if you got colder temperature, the electrons would bounce around a lot less due to the temperature, so there'd be less resistance. So we have a practice problem here. A light bulb in a 120 volt circuit is switched on, and a current of a half an amp flows through the filament. What is the resistance of the bulb? Remember, let's go back to our equation. Resistance equals volt divided by current, or volt divided by amp. So let's see. So we have our volts here, 120 volts. We have our amps, our current, which is half an amp. So resistance equals 120 volts divided by half an amp. Did you see how I did that? I had volt divided by current here, so volt divided by amp. And I had 120 volts and half an amp. That would equal 240 ohms, because volt divided by amp is an ohm. I like saying that word, ohm. The next problem. What current would flow through an electrical device in a circuit with a potential difference of 120 volts and a resistance of 30 ohms? Well, guess what? We're going to have to solve for I, which is current, because we have resistance, which is 30 ohms, and we have volts, which is 120 volts. So, however you guys want to solve for it. What some people have been doing is they will say they'll multiply both sides of the equation by the same thing. So if you multiply the left side of the equation by I over R, and do the same thing on the right side of the equation. So on the left side, I divided by R would leave just I, because the R would cancel. If you do that on the right side of the equation, the I's would cancel. You get volt divided by R. And so then you would have 120 volts divided by the R, which is 30 ohms, which is 4. And what is I? I is current, which is in amps. 4 amps. Okay, and now this is a very broad slide. Going back to electric circuits, they have 3 parts. You have voltage source, which is a battery or a generator. You have an electric device, such as a light bulb or electric motor. You have the conducting wires connecting them. So you have your voltage source, electric device, and conducting wires. You do have to go back to the DC circuit. DC circuits, one wire carries the electric field to the other terminal. It goes through it, and then you have to have another wire carrying it back, because you have to maintain separation of charges so that the electric energy flows through the circuit. So now we just went over DC. Let's look at AC, an AC circuit. For instance, a household circuit. One wire supplies the alternating electric field from the electric company. A second wire is connected to a pipe in the ground and is at the same potential as Earth. So what happens is, when there's a short in the wire, instead of the charge going to you, it's rerouted to that grounded wire and goes into the ground. So AC would still work without a ground, but it's against building codes nowadays to build a house without a ground. So if you want to know how much work is done by a voltage source, you look at its potential. And you'd use that you would say work equals potential times charge, because the coulombs would cancel it and you would just get joules. You would just end up with joules. I'm not going to quiz you on that or test you, but just know that potential times charge equals joules. So you'd have how much work you're doing. You wouldn't have voltage, but you'd have work. So electrical power. This is another equation. Power equals amps times volts, which is watts. So, if you want to solve in this equation, power, which is watts, is on the left side, is going to equal amps times volts. So you need to remember how to work this equation. And I have two practice problems here. So a hairdryer that runs on a 120 volt circuit uses 9.2 amps in current. What is its wattage? Power equals I times V, which is 120 volts times 9.2 amps, which equals 1100 watts. It actually equals 1104 watts, but due to significant figures, since this is 9.2 and this is 120, there's just two significant figures on each. We can only use two significant figures in our answer. So let's go over that again. 120 volts, that goes where the V is. 9.2 amps, that goes where the I is. So 1100 watts. Just multiply them out. So an electric fan is designed to draw half an amp in a 120 volt circuit. What is the power rating of the fan? Let's see. You have half an amp up here. Where's that go? Goes where the I is. That's amps. That's your current. And you have volts. 120 volts. Yep, right there. You just multiply them out and you get 60 watts. So power equals I times V. And here's a table to summarize everything for your information. Let's just talk about a great U.S. scientist real quick, Benjamin Franklin. He explained the electric charge, positive and negative. He did it, and he also proved that lightning was electrical in nature. So magnetism real quick. You need to know that every magnet has two magnetic poles. And if you cut a magnet in two, you're going to get two magnets, and each have two magnetic poles. So even though when you had that bigger magnet, before it was cut in two, the middle of the magnet was not attracted to north or south, because it was the two poles that were attracted to the north and south of another magnet. If you cut that magnet in half, suddenly a north and a south pole are added to those two magnets. And so every magnet's going to have a north pole, and every magnet's also going to have a south pole. So, and also remember that like magnet poles repel, and unlike poles attract. So two north poles put together are going to repel each other. And also know that planet Earth has a good way to think about the magnetism on planet Earth is that you can imagine that there's a huge bar magnet inside the Earth. What's probably going on is there's lots of liquid metal that's flowing around a lot. But the magnetic field of the Earth is different than the geographic field. So the magnetic North Pole is different from the geographic North Pole. That's because the magnetic North Pole, of course, is built off magnetism, which moves a lot. And the geographic North Pole is It's just geographic in nature and does not move. So let's see. So current loops and magnets. Here we got this top line. When a current is run through a cylindrical coil of water, a solenoid is formed. A magnetic field is produced. This is an electromagnet. It can be turned on and off with the current. So you have a switch on this current that's flowing through a wire, and you turn it off. The electromagnet's turned off. You flip the switch back on, the magnet's back on. So now let's say, where does this apply to the real world? Well, electric generators. They convert mechanical energy like steam or gasoline, like if you want to talk about the generator at my house for snowstorms, which we've never used. It will convert steam or gasoline to turn a shaft or a coil in a magnetic field that produces a current. So it uses that magnetic field to produce a current. Pretty neat stuff. 2 slides left. Transformers. A device that steps up or steps down the AC voltage. Voltage is what? Joules per coulomb. So you're going to increase or decrease the number of joules per coulomb. They're going through that line. So how do they do that? Well, there's a primary coil and a secondary coil. Once again, we're talking about coils, kind of like that electromagnet. So an electric field, magnetic field is formed in the primary coil and moves across to the secondary coil. And by doing the number of coils, you can step up or step down the AC voltage. So remember, transformers will step up or step down the voltage. So, to talk about the history real quick of AC versus DC, Edison built the first electric generator, making a DC circuit in New York City. AC motors were not exactly ready yet, so Edison focused on DC. And Nikola Tesla developed a lot of ideas and patents for AC circuits. AC won out in the end. So Tesla and his new company beat out Thomas Edison. Mainly because you could move AC current a lot easier over long distances. DC circuits would burn out a lot and cause lots of fires. Although there was an area of New York City that uses DC circuits. And they used it for 100 years, I believe. And they just recently switched back. So that's the end. I would recommend applying the concepts 1 through 15. I can go over those next week before lab in that half an hour. And I hope this was helpful. Remember that video I would recommend you watch right here. And it's on the slides, and I think I put it on the website. So, good luck. My name is Philip Simpson. Email me at psimpson18@ivtech.edu if you have any questions.